Hello, this will be a demonstration of proposition 10 from book 4 of Euclid's Elements, which requires us to, on a given straight line, construct an isosceles triangle such that the angles at the base are double the remaining angle. Now, the enunciation in the actual text is simply this last part, to construct an isosceles triangle such that the base angles are equal to double the remaining angle. But to make it fit more with how I do propositions, right? So enunciation, given, specification. I've added the given straight line AB. And so on this straight line AB, which we're just going to shoot out like that, and this will be AB. What we're going to do is we're going to construct an isosceles triangle on AB such that the angles at the base are equal to double the remaining angle. Now again, remember that in an isosceles triangle, the angles at the base are equal to each other. So we're going to have, in this triangle, two equal angles which are double the remaining angle. Okay, we're going to begin by cutting the straight line AB at the point C. I'm just going to say C will be about there. But C is not some arbitrary point on AB. There's something very specific about how we cut AB at the point C. We're going to cut it at C such that the rectangle contained by AB and BC, so the rectangle AB times BC, is equal to the square on AC is equal to AC squared. This is proposition 211, which lets us cut a straight line such that the rectangle contained by the whole and the lesser segment is equal to the square on the greater segment. So in this case, the rectangle contained by the whole, AB, the lesser segment, CB, is equal to the square on the remaining segment, AC. Next, we're going to describe a circle, BDE, with the center A and the distance AB. So give me one moment just to figure out how exactly I want to do that. It's going to be a big circle, I guess. It's going to look something like that. We can do that obviously by postulate 3, which with any given center and distance, we can describe a circle. So with the center A and the distance AB, we're going to make the circle BDE. Now next, we're going to fit a straight line within this circle BDE. We're going to actually fit the straight line BD like so. And we're going to call that B. And we're going to fit BD into the circle such that it is equal to AC. Now we can do this by proposition 4.1 to fit a straight line within a circle that is not greater than its diameter, because obviously the straight line can't exceed its. The straight line you fit into a circle can't exceed the diameter. The diameter is the longest chord possible. Okay. So we're going to fit BD within the circle BDE such that it is equal to AC, and E is just some other point down here. It's not even close to important. Okay, next we're going to join the straight lines AD and DC. We do this obviously by postulate 1. And finally, about this triangle ACD, which we have now created, we're going to circumscribe a circle. We do this by proposition 4.5 about a given triangle to circumscribe a circle. So we're going to, how do I want to do this? Like that. It's good enough. And this circle will be circumscribed about the triangle ACD. This is, we can do this by proposition 4.5. I believe this is actually the first proposition where we actually use propositions from book 4. It's kind of neat. This one's also just very different from the other ones. There's no like inscribing or circumscribing. It's just make a triangle. And we'll see why this triangle in particular is important. Okay, so now we are actually done with the construction. We have finished all our steps. And we're going to say that this triangle here, ABD, is the triangle we're looking for. It has been constructed on the straight line AB such that the angles at the base, so the base here is BD, so the angles ABD and ADB are going to be, equal to double the remaining angle BAD. Now, we begin proving this by, we begin with the rectangle AB times BC being equal to the square on AC, right? We cut the straight line AB at the point C such that the rectangle AB times BC is equal to the square on AC. We also know that the straight line AC is equal to BD because we made BD in such a way that it is equal to AC, which means then by a property of magnitude, we can swap out the AC squared here for BD squared because AC and BD are equal. And so we're going to have the rectangle AB times BC equal to DB squared. There's someone in the window. Scared me. So yeah, we have this rectangle AB times BC equal to the square on DB, which then means by proposition 337, it's a fairly long proposition. What it says is that if you have a circle and from some point, in this case it's going to be BD, we're going to have two straight lines falling upon the circle such that the rectangle, contained by the hole and the segment intercepted between the circumference and the point is equal to the square on the other line, then the other line, in this case BD, will be tangent to the circle ACD. So we have something that satisfies the conditions of proposition 337, which means we can safely say that the straight line BD is tangent, it touches the circle ACD. Now, given that BD is tangent to the circle ACD, which is what we have just proven, we know that by proposition 332, that if you have a straight line touching a circle and from the point of contact, you just shoot some chords through the circle, the angles in alternate segments will be equal to each other. In this case, we're going to say that the angle BDC is equal to the angle in its alternate segment, which is the angle DAC. So BDC right here is equal to DAC right there. Again, that's by proposition 332. Which means then, if we add the angle CDA to both sides, by common notion 2, we know that the holes will be equal. Right? If we add equals to equals, then the holes will be equal. That's common notion 2. So we can say that the whole angle BDA right here is equal to the angle DAC plus the angle DCA. Now, the angle DAC plus the angle DCA is not only equal to the angle BAD, but by proposition 132, which tells us that the exterior angle of a triangle is equal to the sum of the two interior and opposite angles. So in this case, we have the triangle ACD, and we have an exterior angle BCD. So we can say that the angle BCD, which is an exterior angle, is equal to the two angles DAC and DCA, which are interior and opposite angles. This is by proposition 132. So we have two angles which are equal to the angle DAC plus the angle DCA, which means that by common notion 1, things which are equal to the same thing are equal to one another. And so we can say that the angle BDA is equal to the angle BCD, like that. Okay. Now, we also know that the straight line AD, which is right here, is equal to the straight line AB, which I'm going to put there. Now, we know that AD and AB must be equal because they're both radii of the same circle, BDE. So by definition 115, the definition of a circle, we can say that all radii of the same circle are equal to each other. So AD must be equal to BA, which means that the angles which these two straight lines subtend will also be equal to each other. So if we take into consideration this triangle ABD, we have two equal sides, AD and AB. So we can say that the angles ABD and ADB are equal to each other, right? Because in an isosceles triangle, this is proposition 1.5. In an isosceles triangle, the angles at the base are equal to each other. So again, the angle ABD is equal to the angle ADB. Excuse me, I'm getting a little lost. Lots of angles. Excuse me. Which means that we have two things which are equal to the angle BDA, right? We have that the angle ABD is equal to the angle BDA. We had just proven that. But we had shown earlier that the angle BCD is also equal to the angle BDA. And so the angle, the angle BCD is equal to the angle ABD. And so all three of these angles, DBA, BCD, and BDA, are equal to each other. Now, the angle DBC being equal to the angle BCD, so that's these two angles right here, these two angles being equal to each other, we know that by proposition 1/6 that if you have a triangle, in this case the triangle BCD, if two angles simply just be equal, then the straight lines which subtend them will also be equal, which means we can furthermore say that DC, which subtends the angle CBD, is equal to BD, which subtends the angle DCB. Right? Okay. We also know that CA is equal to DC. Now we know that CA is equal to DC. Excuse me. I'm getting... there it is. Okay, so we have BD equal to DC. We also know that BD is equal to AC, right? We had made AC such that it is equal to BD. So we have these two straight lines, AC and DC, equal to the same straight line BD, which means that by combination 1, they are equal to each other. So CA is equal to DC. Right, so CA is equal to DC, which means that in this triangle CDA, or ACD, we have two sides which are equal to each other, so this is an isosceles triangle, which means that the angles at the base are going to be equal to each other, which means that the angle CAD is equal to the angle CDA. So that'll look something like that. So again, the angle CAD is equal to the angle CDA, which means that if we add the angle DAC to both sides, we know that the angle CDA plus the angle DAC must be equal to double the angle DAC. This is common notion 2. It's a little difficult to figure out because you have the double in there, but it's still common notion 2, right? We're still adding the angle DAC to both sides of this, so if equals be added to equals, then the wholes are going to be equal. So we have that the angle CDA is equal to the angle DAC, or no, yeah we do. I mean, that is true, but it's more important that the sum of the angles CDA and DAC is equal to double the angle DAC. Now again, by proposition 132, right, we should recall that the angle BCD is also equal to the angle CDA and DAC. Right, so this angle here, BCD, is an exterior angle to the triangle ACD, which means that it is equal to the sum of the two interior and opposite angles, in this case CDA and DAC, which means that we have two things which are equal to the same thing. So common notion 1 tells us that these two things must be equal to each other, and so we can say that the angle BCD is equal to double the angle DAC. Now finally, we know that the angle BCD is equal to both the angle DBA and the angle BDA. Right, we had shown that here in step 6. So the angle BCD is equal to the angles DBA and the angle BDA, which means that both of these angles, DAB and BDA, are also equal to double the angle DAB, which is the angle DAC, right? So DAB is just the same as the angle DAC. And so in this triangle, ABD, we have the two angles DBA and BDA at the base, which are equal to double the remaining angle DAB. Now, such an isosceles triangle, ABD, is what we had set out to construct. We were given this straight line AB, and upon it we have made the triangle ABD such that the two angles at the base, DBA and BDA, are equal to double the remaining angle DAB. Now this is, of course, what we set out to do, which means we're done with the proposition QEF. Now, you can do a little bit of math to figure out the precise degrees of the angles within this triangle. You'll find that it's a 36, 72, 72 triangle, which is, kind of neat. You don't get to work with precise degree measurements in Euclid, so it's always kind of neat to do them when you can. We'll see in the next proposition, 4.11, why such a triangle is important. We're going to discover that this sort of a triangle is important to the construction of a regular pentagon. And this being what proposition 4.11 is all about. I'm going to end the video here and move on to that proposition.